Hello, everyone. Welcome to the first Ontario2 stream here at today's FTC Kickoff. For this next session, please welcome 2020 Ontario FTC Dean's List finalist Armand Sergupta with an OnBotJava workshop for TeleOp.
Thank you. So as Sherry mentioned, we're going to be going into how to program your TeleOp with OnBotJava. Okay, so can you get the next slide? And that's basically what this says here. The thing you need to understand about this session is, if you watch the previous session where I talked about the different tools, different programming tools, in this session we're going to be using Java. So Java is, again, for those who didn't tune into the last session, it's a text-based programming language, which is an industry standard. And if you don't have an understanding of the concepts listed on the right-hand side, it'll probably be hard for you to follow along with this tutorial. There's another one with blocks, which you can go watch that if you do not understand Java. Additionally, if you want to follow along directly, you'll need to have your phone set up already. Otherwise, you will not be able to follow along. But with the last one, you don't really need to have your phone set up, but you'll still get the learning experience and remember the content for when you do have your phone set up. So can we get the next slide? Okay, so what we need to understand first is what do I mean when I say teleop? So a teleop is a type of OpMode. And there are two types of OpModes. There's autonomous OpModes and TeleOp OpModes. As you can see from the images, in a TeleOp OpMode, you are meant to use your controller to drive around your robot, and in an autonomous OpMode, you're not allowed to use your controller. The robot has to do everything based on pre-programmed instructions. And also, you can see in the competition setting, a TeleOp OpMode lasts for 1 minute and 30 seconds, and an autonomous OpMode lasts only for 30 seconds. So, get the next slide. Okay, so for today's goal, what we're going to be trying to do by the end of this session, or by the end of half this session, is the first goal is going to be to drive the basic bot. That means to get it moving, just get the drive base moving by using our controller. So that's what we want to aim, and now we're going to be that's what we want to achieve. And that we're going to be talking about how to do that. Okay, so the method I chose to implement this is a tank drive. That means that the Y value of each joystick controls the motor power of each wheel. So as you can see from the diagram, the red joystick, or the leftmost joystick, controls the leftmost wheel, and the rightmost joystick controls the rightmost wheel. What I intend to do is, if you push the right joystick forward, then the right wheel goes forward. If you push it backwards, it goes backwards. And the same thing for the left wheel, but of course corresponding to the left joystick. So that's what we want to achieve. Okay, so we have an issue in trying to achieve this. The first issue is that our controller has unintuitive values. Now, most people would think that going forward would be positive. So if you push the two joysticks forward, that would be positive, and if you pull them back, it would be negative. However, this Logitech controller, which is standard for all FTC use, is the opposite. So that's the first unintuitive, that's the first problem we need to keep in mind when programming our robot. But we'll just keep that in mind, and when we're coding it, we'll go into fixing that. The second issue is a reversed motor. This means because when you're building your robot, your two motors are facing in opposite directions. That means what's forward for one motor is always going to be backwards for another. In this case, what we would typically consider as forward would be the right wheel would be correct and the left wheel would be wrong. It would be reversed. So when we tell it to go forward, it's going to go backwards, and vice versa. So that's the second issue we want to keep in mind. And so when we're coding it, and this is how we're going to start coding it, is we're going to set it up. As I sort of mentioned in the previous presentation, you go to this web URL, and you can go to you click OnBotJava, you create a new code, or you can upload a pre-existing code. And this is sort of the setup. You just want to get a teleop code with a blank linear out mode, and you can check the box to say set up code for configured hardware if you want the editor to automatically define all your motors and sensors that you already went ahead and defined when setting up your phones. Okay, so program structure. This is basically the 6 things that we are going to focus on in our program. The 6 important sort of areas or sections that occur in our program. So I'll read them out to you. So first is you're importing your objects or your classes or whatever other external packages you're importing. That happens at the top of your program. Then you globally declare motors and variables. Again, these are all concepts that you should be familiar with if you know Java. And we declare those next. Then we define those variables by mapping it to the physical port on the robot. We then initialize the code. my mistake. We don't initialize the code. This is where we put initialization code. So anything that we want to happen once we've clicked the play button, but not yet clicked this run button. And then we, of course, have a run code, which runs one time after the run button is pressed, and our loop code, which is going to keep running as long as the op mode is active. Next slide. Yeah. So this is sort of the this is a sample program, a blank program, and this is each of those sections labeled out. At the top, you can see all our different imports, and those are all the different objects or libraries that we need to reference the motors and such. That's already been written for us. We're just leveraging code that's been written for us by first. The next section, section number 2, is you can see we're globally declaring our motors, and you can see that's a global declaration because it does not happen within a function, but instead happens at the class level. Next, we define them inside the function, but since they've been declared globally, they'll remain global. Just the value has been updated locally. Then the fourth section, this is the initialize section. This is again where you put the initialize code. You can even see the telemetry, which is basically printing. So if you're familiar with printing in Python or logging in Java, you're printing something to the terminal. In this case, the terminal is the driver station phone. So that's what you're basically saying status initialized. It's just a kind of a reminder or a debugging step that most programmers use. And then after that, the fourth step is the run code. So right after the telemetry to update and before wait for start, and that will be the run code. And then finally, really the most important part that we need to look at for teleop is number 6. Sorry, so the run code would be number 5. That's my mistake. It would be after wait for start, and then the loop code would be number 6. So that would be everything in this while loop, and you can see it's appropriately named loop code because it's going to keep looping inside that while loop until our program is done. So you can sort of see the breakdown of the program based on those words. You can see them labeled here, each section of the program. Okay, so here are some useful commands that you're going to want to know for programming a teleop command. The first one is how to power a motor. You can't drive your robot around if you don't know how to power the motors. So powering a motor is very simple. All you do is type the motor name dot set power and then the power level, which is a value between -1 and 1. For example, if you want to set the left and right motor powers, you say left motor dot set power 1, right motor dot set power 1. Which is going to cause them to spin at full power because that's the range from -1 to 1 forward, at least relative to themselves. It's going to spin forward at full power. And then the next important value or command you want to understand is the get joystick value. So the way you do that is you say gamepad1 and then .access, where access is the name of the joystick, trigger, or button you're trying to access. So, for example, we want to get the left and right Y values of the joysticks. So in that case, we say gamepad1.left stick Y and gamepad1.right stick Y. And gamepad1.left stick Y would be the left joystick that we were talking about to control the left motor, and the right one would be the right joystick. So if you remember the picture, if that helps you, left was the red one and right was the blue one. Then we also need to store this value because if we want to use it later on in our program, we do want to store it into a variable, and this should be very familiar syntax to you if you're aware of Java. And keep in mind that it's a float because it's from any value between -1 to 1. It's not just -1 and 1. It's a whole range of floats in between that range of the numbers. Okay, so we know those two commands. We know how to get the joystick values, and we know how to power a motor. What we need to do now is take those two things and combine them so we can power the motors from the joysticks. So what we want to do is we want to set the motor power equal to the analog value from the joystick. The left motor to the left joystick and the right motor to the right joystick. Because that's what we were trying to do at the beginning, right? That was the goal we established. Right? So this is what that looks like, right? We have our motor power command in the outermost section, left motor and right motor to set power. And then, respectively, we take the joystick value, the gamepad1.access, and in this case, the access is either left stick Y or right stick Y, and we set that equal to left and right motor. Now, if you recall, the values of the joystick return is from -1 to 1. So it's a perfect match, and we're not required to remap or sort of shift the numbers because it's already a perfect match, and we can directly go ahead and plug that in. Except for, keep in mind that our two issues that we had, we will have to accommodate for those. But now we need to think about, so we have these two commands, but where in the program do we put it? We have 6 different places we can put it in the program, correct? Where do we put it beside imports? Do we put it in the loop code? Do we put it in the run code? So we need to think about where do we put this command in the code such that it does what we want. So where we're going to want to put it is within the loop, within section 6. So you can see this is the code right over here. It's right above the status running code. This is the previous outline I showed you before. And we want to put it right above the status running in section 6. You can see those two lines of code that we just talked about. And the reason we want to do that is because if you recall how each section works, section 6 keeps looping until the program is stopped. And that's exactly what we want. If we put it anywhere else, it would only, regardless of whether it would compile or not, because it would be a syntax error, logically, if you put it anywhere else, it would simply run for the shortest amount of time, maybe a millisecond or less, because the computer goes so fast. It would go over that, and then it would never come back to that, which means the motor powers won't be updated and the joystick values won't be updated. So nothing will happen. It'll seem like nothing will happen. It'll happen for a split of a second. But if we put it in loop, every millisecond or less, it'll be updated with the correct joystick values, and it'll update the motor powers. So that'll keep working until we've stopped the program. And that's why we need to put it in section 6, because it's the only section of the code that actually loops. Okay. Next thing, we now need to fix those errors we talked about before. So fixing the errors of the joystick should be fairly simple. We want -1 to be 1 and 1 to be -1. We're just flipping the values. Simply putting a negative sign in front of gamepad 1 .axis will flip the values, making, if you recall basic math, negatives positive and positives negative. And you can see that if you look down below that, we have those values, and now we're setting them back to the motor. So that's the final command. We're taking those negative values and setting it back to the motor powers, so it's correctly scaled in our heads, so that forward is forward and backward is backwards, not the other way around. On the other side, we have our other problem, or issue number 2, which is that we have one reversed motor. Since that motor is reversed, what we can do is there's a nice command called left motor, or whatever motor you want to flip directions. So the motor you want to flip directions, set direction, and then DC motor simple direction reverse. It's a long command, but again, that should autofill, or you can look up the syntax online. But in this case, the direction of the motor we want to flip is the left motor. So you can see that we wrote left motor set direction, DC motor simple direction reverse. And it kind of spells it out for you right there. We're flipping the motor. So if we send negative power, it's going to go forward. And if we send positive power, it's going to go backwards, at least intuitively to itself. But from a grand scale, from an outsider's perspective, it'll now do the thing we want, which means when we send power, for us, it'll look like it's going forward. And when we send negative power, it'll look like it's going backwards. Okay, and you can see where we'd put that in the code. We would put that right with the initialization code, because we only want that to happen one time, and we want it to happen once the program has been started. And not to continuously occur, because that's a waste of memory and waste of resources, and we don't need that to happen. Okay, so this is putting it all together. You can see those two commands, as I mentioned, where we're putting them. The first one is the flipping of the left motor, and again, we're putting it in the initialize section because we don't want it to loop, and we're putting the negative signs, our negative fix, right with our code, which is already in the loop section, because as previously mentioned, we do want that code to loop. And so that fix has been implemented in the correct spot, and so has the flipping of the motor direction been implemented in the correct spot. Okay, so finally, once we've made all these once we wrote this code, we fixed our issues. Now what we can do is we can upload and run the code. So all you have to do to do that is click the wrench icon, and then go onto your driver station phone, click the corresponding op mode, and click the play button and then the run button, and your code will be running. But it won't do anything if you're not connected a controller properly. Your code will be running, but it won't be able to find the controller. So to connect a controller, you need to connect it to the adapter, your OTG adapter that comes with your phone, and then plug that into your phone. Once you've plugged it in, you want to press the start and A buttons simultaneously, and you'll see a white icon appear on the top of your driver station phone. Additionally, you want to make sure that your controller is switched to the X position rather than the Z position. If it's switched to the Z position, it might not work correctly. Okay, so by running that code and connecting the controller, we achieved our first goal of driving the robot. That's working. Now, let's say we get a little bit more advanced in our robot. We have a new goal now. We want to move our arm. Okay, so we need to think about how we're going to do that. For the driving the robot, it was pretty obvious. We used the two joysticks. Here, I show you a bunch of the different circles, a bunch of different buttons that we could theoretically use to move the arm. So we really need to select which one you think would be the best for your own hands and how you prefer to drive. For me, those are the left and right bumpers. That's what made the most intuitive sense to me, and that's what I'll be using to show you how to move the arm. Now, you can use any other buttons you want, but this is just a matter of preference. So now that we've decided we want to use the left and right bumpers, we need to decide which one will move it up, which one will move it down. In my head, the right one should move it up, and the left one should move it down. It's shown to you in the diagram with the blue arrow pointing up and the red arrow pointing down. So that's what I want to achieve. That's where we're going to go about setting to achieve now. Okay, so the first thing we're going to do is we're going to declare our motors. We saw how the program did it for us automatically. If you started the code previously, it would not done. If you configured your sensors after you made the program, it's not going to do that for you. So this is how you do it. Just copy the format you saw the program do for you, which is declare the motors, define them, and then put them in the correct spots. You can see all those examples down there. That's pretty straightforward, and you're able to see how it's very similar to the setup of the left and right motors. Okay, so now we need to think about what we want to do. We want to think if the right bumper is pressed, lift the arm up. If the left bumper is pressed, lower the arm. And if neither is pressed, do nothing. And we want full power let's say we want full power when going up because we're fighting against gravity, and only half power when going down, since gravity is going to be helping us move that arm down. So if we write in the code, this is our first implementation to code. We say that if the right bumper is pressed, go up. If it's not pressed, don't do anything. If the left bumper is pressed, go down at half power. If it's not pressed, don't do anything. So that's our first sort of implementation to code. So, but when we do this and we go ahead, we upload our code and we plug in our controller and we run the program, and just like how we did before, we'll notice that although the drive is moving now, the arm is not moving. So why? Why is our code over here not moving? Or not working, rather? Why is the arm not moving? And that's what we're going to need to troubleshoot. What is wrong with this code? Okay, so a really good strategy of figuring out what's wrong with your code is picking just one scenario in your ifs, your elses, your loops, all that. Just pick one scenario with starting variables and run through the program as if you were the computer. So at the top, we can see all the different scenarios we have here. We have all the different iterations for left and right bumper. So it's either 0, 0, where both of them are 0, then we do nothing. If right is 1, we go up. If left is 1, we go down. And if they're both 1, well, why would you ever do that? You wouldn't reasonably press both of them at the same time. That's not a use case that a driver would actually implement. So realistically, the 3 we're looking at is if neither is pressed, if right is pressed, or if left is pressed. We already know that doing nothing is working. Apparently, that's not the issue we're trying to solve. We're trying to make it go either up or down. Neither is working currently. So let's highlight that section. Within that section, as I mentioned, you have to pick one. We can go through both, but for the beginning to see what's wrong, we'll need to just pick one. And since neither of them work, it's equally valid to pick either of them. So once you've picked one, understand what this means in your code. This means that if left bumper is 0, the check that we were initially checking before, if left bumper is pressed, will become false, and the right bumper will become true. That's what the value represents now. It turns from true to false. Sorry, the left bumper becomes false, and the right bumper becomes true, because left is 0 and right is 1. Okay, so now we have that new updated code. Instead of the dynamic values, it's just a fixed true and false. So let's see what the code does in this situation when left is false and right is true. Okay, so we have the first statement that's true. So what we're going to do, what the computer is going to do is the first statement's true. So it's going to execute arm.setPower1. Because the first statement was true, it entered that if statement. It's also going to go to the next if statement, and since it was false, it's not going to execute the go down by 0.5. It's instead going to execute the stop, right? Because the left motor, the left button is not pressed. So this is the important step right here, and everything at that point sort of kind of goes down the line. But the important thing to recognize here is the first if statement and the second if statement are separate. So the first one, it's true, so it's setting the power to 1, which is what we want. But then the second one is false. But it's not taking into consideration that the first one was already true, so it's stopping it because the second one is false. So if we kind of simplify that down, what we get is turn it on and turn it off. Turn it on or turn it off just means turn it off, and that means do nothing. And that's sort of the problem we're getting here. That's why our arm is not moving, because we're giving it conflicting statements. We're telling it to turn on and turn off. Because if you think about it, you're either going to have the left one pressed, the right one pressed, or none. If you have none pressed, well, that's great. It's going to do nothing. But if you have the right one pressed, the left one will turn off. If you have the left one pressed, the right one will tell it to turn off. So in all cases, you're turning it off and turning it on, which basically equates to turning it off. So let's find a solution to this problem. What we can do, instead of having the segregated if statements, is we wanted the if statement to consider the first one. So we can use an if, elif, or sorry, in this case for Java, else if structure and else. This will consider the first one. And if you're familiar with how Java works, you'll be able to see why this statement works. It's because only one of these three functions can be executed. Only the arm can either be set to 1 or negative 0.5 or 0. Never two of them at the same time, or never three of them at the same time. Just one out of the three. So in this case, it works because it'll either be up, down, or nothing. This is the correct way to implement the arm. So when we put it all together, in the top we have our driver code. We now have our updated ARM code, and again we have our loop code and our status running, just to keep kind of track of where we are in the program currently. So we can see that's where our ARM code fits into everything else. As you would assume, just like how the driver code fit into the loop, so does the ARM code. Okay, so let's recap what we just did. We dictated a robot's behavior with the controller. This is called TeleOp. Certain operations require analog inputs from the controller, like driving, because you don't want it to go full force forward at all times and full force backwards. It's a range, and the joystick kind of decides how fast that is. But others might not, like the arm. The arm is either going up or it's going down. You don't really have a need to control the speed dynamically. You can find a set value once in the code, and it can be like that for always. Okay, so another thing that we learned is where the code goes in the program is important. If we put all the code would have been correct, and the same code that would have worked in the loop section, if it was put anywhere else, it would not have worked. So where the code goes in the program is important, because it'll do different things depending on that. And the other thing we learned is if we think like the computer, we can fix many errors. So the strategy we used at the beginning, it seemed like that code would work. Or to many of you, it might have sounded like that code would have worked. But then we broke down the situation, we took a specific event that would happen, and we ran it through the code, and we figured out why it's not working. And at that point, it became much easier to find a solution when you already know what's wrong. Okay, here's some other helpful tips that might be a little advanced for a lot of teams, and this is maybe what some of you were looking for, how to improve your teleop game. But the first one, everyone can achieve. Just like how we thought like the computer, we can also use telemetry for debugging. So thinking like a computer is one strategy, and using telemetry is another strategy. In fact, we can even have used telemetry for this code itself with the ARM situation, and we would have been able to figure it out. For example, if we checked what motor power we were sending, if we printed out to the telemetry what motor power we were sending to the ARM motor, we would have seen that we were frequently switching between 0 and 1, or full power up or no power, or if opposite or it would be negative 0.5 and 0. So we're turning it on and off, turning it up and down. We'd be able to see that in our telemetry, because we'd be able to see that value is switching so frequently, and that would have helped us come to the same conclusion. So telemetry is an equally powerful tool for debugging. And again, telemetry is just printing to the console. That's all telemetry is. Okay, now this is more of the advanced tips that you're going to want to use if you're trying to take your op mode to the next level. You want to use sensors to assist the drivers. For example, encoders to detect intake jams. If your intakes are spinning and let's say last year's game, the Sky Stone, if it came in at a weird angle, it's possible that your intakes could have gotten jammed. In that case, the encoders would stop spinning and you detect the jam. You could possibly outtake and re-intake again. So the driver does not have to do that. That helps speed up your driver. It helps speed up your teleop routines so much, because if the computer can take care of certain things, then the driver can focus his attention on other things. And that's basically what the rest of the tips, that's what the 3 to 6 tips are going to be showing you, is how to take the load off the driver so he can focus on other things. He or she can focus on other things. So the distance sensors is another, sensors in general. This is what we're talking about, how to use sensors to make the driver's life easier. So first we talked about encoders to detect intake jams, for example. We can use distance sensors to automatically move a lift to a correct height. so the driver doesn't have to kind of hold that button down and eyeball it. You can have like presets on that lift, so it'll go to the correct height. You can have a single button represent a sequence of events. So for example, if you have a lot of motors moving and a lot of servos moving to intake and then pick up the stone, but again, this is an example from last year's game, you can have that all represented in a single sequence. So the driver does not have to control manually multiple motors. Again, it speeds up the driving process. I think I'll skip the final one, and that's experimenting with scaling power values to achieve more control when driving. So currently, we're not scaling power values at all. We're just going from -1 to 1, and we're just directly applying that. But what you'll notice is it becomes very hard to control your robot at slower speeds. So what you might want to do is have your values transformed into a different function, so that you have more choice when it comes to the slower ranges and less choice when it comes to the higher ranges. And you can do that through many methods, like functions such as logarithms and things like that, and exponential functions will help you sort of kind of smooth that out in the beginning. So you have more x values to represent your y values, x values meaning the joystick, and the y values meaning your motors, so you can control it at lower speeds. That's another idea to use when trying to achieve more fine driver control. So those are some helpful tips. 2 to 6 is really for once you're trying to take your TeleOp to the next level. But number 1, all teams should be doing telemetry using to debug your code. Something's not working. You want to figure out why it's not working in OnBotJava. The best thing you can do is use telemetry, and then once you see what the telemetry is doing, you can think like the computer and figure out why it's doing that. Next slide. Right. So that brings us to the end. Those were our tips. We ran through, we recapped and we ran through our tips. And now I want to see if any of you guys have any questions, and I'll be glad to try and answer them.
I don't have any in on the chat yet, unless somebody puts one in right now for us.
All right. So again, if we want, we can, in the remaining time that we have left, we can sort of talk about how we can talk. I kind of briefed over the TeleOp. How to improve TeleOp. Those helpful tips, I kind of skimmed over them. But if we want to go into more detail about how TeleOp can work in an improved setting for highly competitive teams, I think I'll start talking about that now if no one has any further questions. Give it a second so we can look at those tips on screen as well. And really what these tips are going to help you do is increase the amount of points you can score in your driver routine, because it's going to take the stress off your driver and let them focus on driving or getting to it, driving the base of the robot or on the higher level functions rather than worrying about each motor's position. Okay, so again, what we covered today is we dictated a robot's behavior with the controller. What does dictating that robot behavior with the controller means? That means that you're going to make the controller, the certain buttons and joysticks and triggers on the controller represent different functions on your robot. That can represent just one motor, or it can represent a cluster of motors. And that's one of the advanced things that you can do, is have a single button, as we discussed a little bit ago, represent many motors, and it's sort of a subsystem altogether. So that's all working together. So the driver doesn't have to individually control those motors. And now you also need to think about which operations on your robot are going to require analog input and which ones are going to require digital inputs. Driving is something that almost always universally requires analog inputs. So those joysticks will be taken up for that. But you also have triggers, which give you analog inputs. So if you need triggers to move, maybe it's really important to you that your lift is moved smoothly. In that case, you probably want to use analog values. Additionally, if you feel like you only have 4 analog, so you have your 2 joysticks, and then you have your 2 triggers at the front of your controller. Those are all the analog inputs you have. If you're finding that you're running out of analog inputs, there's different methods of driving that'll only use 1 joystick, and that's called arcade drive, or it's often called arcade drive by many teams. And that's where when the front and back controls both motors and the left and right controls the turning. And then that frees up another joystick for you to move any other subsystem through an analog fashion based on 2 more axis, because remember that each joystick not only can go forward and backward, it can also go left and right. Okay. where the code goes in your program, that's pretty simple, especially if you're coming to this level of integrating subsystems to one button and having analog values control certain subsystems. At that point, you'll have a fairly good understanding of where your code's going in your program. Those 6 sections you'll know by heart. You'll not only know them, you'll have an intuitive understanding of how they work. So, and really the important thing, I think a lot of people, once they find an error, they don't know what to do. They might ask for help. They might ask their mentors for help, which is great. But you do want to be able to figure out how to figure out issues on your own. And we covered one strategy, and I talked about another one. Again, if you think like the computer, you can fix a lot of errors. It's not that the computer is not doing what you asked it to. It's that you asked it to do the wrong thing. Even though it might make sense to you, it does not make sense to the computer. So again, with the example of that if state, those 2 separate if else statements, it looked like it would work, but it didn't. And so we thought like the computer. We figured out why it was doing what it was doing, and then we changed it to correctly fit the computer's language. Again, another way we could have done that is through telemetry. Telemetry was printing to the console, and we could have seen the values are flipping on and off, and that would have given us an indication of what's wrong. So both those techniques are very valuable and very powerful when it comes to debugging and troubleshooting our programs. If you get the next slide. Okay, so now specifically what I want to talk about here in kind of taking your teleop or your code to the next level is how can you use sensors to improve your program. I know I touched on it a little bit before, but there's a lot more examples of things you can do. And with the game reveal coming out shortly, you'll be able to kind of think about how you can apply those techniques to make your teleop runs much more efficient. So yeah, intake gems, super important. You can detect them. The code can fix it by itself. The driver does not need to waste time trying to get whatever game object out of your intakes or unintake or outtake, sorry, and then intake back again. That can all be done by the computer or by your code rather. So that takes the stress off the driver. Also, an example of a way to use sensors that our team did in the Skystone season is we had a touch sensor so that when the Skystone entered the robot, the touch sensor would be pressed down. That would let our code know that the Skystone has successfully come into a robot, and then it would automatically stop the intakes. So the driver is not required to stop those intakes manually. He just needs to drive, gobble up a Skystone, and the intakes will automatically stop. So it's not constantly ramming the Skystone into the robot. So using sensors in that way to kind of automate actions is very valuable. And so you have to use many different sensors like encoders, distance sensors, touch sensors to understand what's going on with your robot and whether or not your code is confident enough to make a decision to do something on the driver's behalf. Again, this can also work in the opposite way. If your sensors are malfunctioning or your code is not written well enough, then your code might be hampering the driver's performance because the driver is going to be fighting against the code to make it do what he or she wants. Presets on lifts is something very important. If there's, again, not every game has a lift or requires a lift, but this year's game, or rather last year's game, the Skystone game, there was different heights you could place Skystone, and every time you place a Skystone, you have to go one Skystone length higher. So having that automatically calculated is really helpful. So maybe you just have one button that takes the lift for the right height because you know how many Skystones you've already placed. And your program calculates based on how many Skystones you've placed, how high you need to go. Now the driver doesn't need to hold down a button and kind of eyeball where the lift goes. He presses the button and the code takes it to the exact correct spot. That saves on human error, and it saves on the driver having to think about that thing. He can think about something else. He or she can think about something else like moving the foundation or putting the Skystone on. So things like that really help the driver clear up his mind, the driver's mind to do something else. Okay. Another example is so. By the way, one of the great ways to figure out what you can do to improve your teleop code is to look at what other world class teams have done to make their teleop code functional. And really how they became the best. So, for example, you can look at teams like Gluten Free or Wizards.exe, and they have many videos posted, or you can even watch their match videos and sort of get an idea of the techniques they use in their teleop programs so that they are able to move so quickly and so efficiently. And I've been told we have some questions, so I'd love to answer those now.
Okay, what are the plans for your team this year as a remote team.
So first of all, our team is a community team, meaning that we're not affiliated with a school. So that might be very different for you, for the person that asked this question. You might be affiliated with a school, in which case you would have a whole different set of requirements that you'd have to meet, and you'd be held accountable by your school. Being a community team, we sort of the decisions that we make are sort of in our own hands. That being said, we will of course have the correct safety precautions in place when building, and we'll try to minimize number of members coming to the session, so kind of have alternating days, and of course hand sanitizer, masks, all that stuff. So that's the basics. But in terms of a high level overview of what we would do, we plan to have alternating days where team members come in, and that will sort of help keep it to a respectable number of people in the building area. And anything that we could do virtually, we will do virtually, such as making the CAD for the robot, the programming for the robot, the designing for the robot. All those things that can be done virtually will be done virtually, and only when we need to come in to build will we build. And even then, we can have people on Zoom calls, or we can call them, and we can have only one person building and everyone kind of telling them what to do. And again, that's really going to be a challenge for sure. No one likes getting yelled at about you're putting the caption in the wrong way, but that could be one of the solutions if you're only able to have one person there. In terms of, you're talking about a school, if you are a school, that's a lot more tricky, and it's dependent on what your school deems as safe and not safe. And you'd have to talk to your principal, but in general, you have some strategies, and First has posted strategies of how you can run a team during COVID-19. And I do believe there's a presentation that has already gone or is currently going on about how to run a team during COVID-19.
What piqued your interest to get involved in programming on the team?
So I joined First last year, like many of you in Ontario, FTC. I joined it only last year, but I'd been the programmer from other robotics teams from quite a while, and it was half out of necessity, half out of because I wanted, because I've been doing it for a long time. So perhaps the better question is what got me into programming in the beginning, and really how it worked for me is programming was something that I could go home, I could learn about, I could do by myself. And that did not require the robot to be there. And when there's a lot of people on your team, which is similar to how my team was in the beginning, it was hard to get time with the robot and get to build it. So programming is something I could look about, I could learn on my own time at my house, and that's sort of how I got into programming. And then on my FTC team specifically, I was likely the best candidate to program, I continued on programming for my FTC team, and of course spreading that knowledge so I can get people to help me.
Now that you have competed for a year, what did you learn that will help you this year?
So what did I learn from last year that'll help me this year? Right. So we learned a lot last year. In terms of lessons learned, there's been a lot. There's so many technical examples I could give you, particularly pertaining to the building system, which is completely new for me and for all of my team, primarily the Tetrix building system. But on a bigger scale, or sort of a more applicable scale to everyone, we learned that programming and practice should not be pushed to the last week. You do not want to keep building and building and building forever, and then you kind of cram your programming and practice time into the last week. Because even if you have the best robot in the world and you have no practice driving it, and you have no good autons, especially in FTC, where autonomous is so important, and you have no driver practice and no good autons, you will not succeed even with the best robot in the world, because the driver practice and good autonomous routines are vital. So what I learned from last year is leave time, even if that means sacrificing on certain components of your build, for practice and autonomous. That's the biggest thing I learned from last year, for sure.
How many autos did your team have last year, and will you have more this year?
In terms of how many different autonomous routines, I think we had a different one for each side, each color side. But in terms of unique, in terms of what they tried to accomplish, we had 2 separate autons. And as I mentioned last year, we kind of crammed all that auton stuff towards the end, so we barely had any time to get into it. But we just had one auton that would park over the line, and one auton that I think delivered a sky stone, not a sky stone, a normal stone, and then delivered it on the other side and came back and parked on the line. We also made an auton to pull the foundation out and then go park on the line, which is also an auton we made at practice. But then during the competition, our foundation grippers broke, so we were not able to use that. So technically, we had 3. We used 2 at the competition. This year, I plan to have many options. Again, as I mentioned, this year I plan to have a lot more time to do autonomous. So I do plan to have many options in the autonomous routines I have. Again, you don't want to have too many because then it becomes a little bit hard to choose at competition. But I do want to have a significant variety of choice, so that if our teammates, again, a good thing about having different autonomous routines is if your teammate has a routine they want and your routine conflicts with theirs, you can just select another routine. And even though it might get you less points, collectively your alliance will score more points. So that's the advantage of having different autonomous modes or different autonomous routines, is because it's mainly for interacting with other teams. You can just make your best autonomous routine and you can always run that if it was just you. But when you're interacting with other teams, you do want to have different options available so you can accommodate those other teams.
What is the most common issue teams run into when programming for TeleOp, and how can they overcome this?
I'll tell you our biggest issue that we ran into. It was programming our mechanism wheels. And funnily enough, it was you might think it's a programming problem, but oftentimes it could be a mechanical problem. I think, and generally, holistically, that's probably one of the biggest problems teams could run into, is they'll keep trying to fix the code, but if the build is broken, the code can do very little to help it. So that might be a large source of frustration. That might be a common mistake teams make. It'll often be said the programmers need to fix it, but if the build is broken itself, the programmers cannot fix it. So I'll give you an example with our mechanism wheels. The code was all fine. We checked it several times on different forums, and that was the standard code. But the issue was the weight distribution on our robot was uneven, and that was causing the mechanisms to not strafe properly. So that's a build issue, and you'll often see programmers. This is relating to both autonomous and teleop, but you'll see programmers trying to fix issues that are not theirs to fix. So I think that's the biggest issue.
Does your team share your code with other teams?
If we made, so our code is on GitHub, but we don't promote it too much because, as I mentioned last year, it was fairly simple in terms of what it was doing. It was not really going to help many people. But we don't hold back to show our code. It's just that we don't advertise it so much because it's not that helpful. But there's no sort of secrecy behind the code. That's all open. If someone wants to see it, that's 100% okay. In fact, I think in the previous presentation, I had a slide with our team's early block code just to show how messy it got. That was the example. But yeah, there's no reason to sort of hide your code. I think most teams do make their code publicly available. And you'll see teams like high-level teams often talking about their code. And we do the same. It's just that last year our code wasn't at that level where we thought it would help many people. So we did. It's released, but we did not advertise it too much.
Okay. Do you put a lot of remarks and comments in your coding?
Yes, for sure. And that is something you definitely should be doing. Commenting your code is super, super, super valuable, especially if you're working with more programmers, because if they don't know what you were doing, it's going to be ridiculously hard for them to fix your code. So commenting is very important, and even just for yourself, because oftentimes you'll come back and you'll read your code and you won't even remember what this code was trying to do, because that's what happens with time. So if you leave those comments and you explain what's happening, it makes it much easier to debug, especially if you're switching people or you're coming back to your own code after a little bit of time. So commenting is something that we absolutely do. It is something that hopefully you as your team will do as well, because trust me, it'll make your life easier when you come back to your code. Even if you're looking at, so let's say you start a new season, this year you're going to be starting a new season. If you go to look back on your old code and it's sufficiently advanced and it has no comments, it's not useful to you. You cannot salvage that code. You cannot copy that code over because you don't understand how any of it works. So you have to work from the ground up. Comments are super valuable in helping you to understand how your code is working. And again, that is itself is valuable because you're able to reuse code from year to year.
Do you have coding classes at your school? And if you don't have them at your school, how do you learn Java?
Okay, so yes, we have coding class at our school. We have a club as well as we have the actual courses. I think most high schools would offer those courses, computer science courses. For some reason, if you do not have that course or do not have the availability in that course, there are tons of resources online for Java. Less so for OnBotJava, but for Java in general, there's absolutely hundreds of resources. If you just simply Google Java tutorial or learn Java, you'll find an ample of resources able to help you. Some off the top of my head, I think would be W3 Schools is a website that's really good for teaching not just Java. It teaches almost every language, but Java included. And there's many websites like that that are there to help you learn Java. And if you prefer videos, there's also tons of YouTube videos and YouTube series that also have people talking to you and explaining it. So there's a lot of resources online to learn about Java. And if you want to learn about FTC specifically, there's also you should look for teams that provide those resources, and they probably won't delve into how the Java works. So you need to learn the Java first, which is kind of open to everyone regardless, and that's a skill you take with you outside of first for sure. And then you can look at specifically how that pertains to FTC, and you can learn the teams, like even First itself also puts out a bunch of videos about how to program, but it doesn't really go too advanced. So if you want to go advanced, there are many high-level competitive teams that do post. I think namely Wizards.exe has a great tutorial series. For example, on Vision, they have spell books on Vision. They have spell books on odometry, which are really advanced programming concepts, which you can all learn. So the best way for you to learn for FTC is through other teams. The best way to learn Java in general is, well, you have the entire internet at your disposal, and there's tons of resources for that. Are there other questions?
The last question that I have is, how is the season going to be different for your team this year?
So of course you have the whole COVID situation going on, and that's definitely going to impact our team for sure, and even more so school teams. So the way it's going to impact it is because we're going to be staying home a lot more. We'll have to get good at virtually communicating, and that it'll definitely hinder progress because it's much easier to do things when you have a whiteboard in front of you and you're talking to someone with you physically. So it'll make things definitely harder. But I think there's a lot of strategy and a lot of talks going around right now, even about how you can manage that. And I believe First has also extended this season, so we have more time because they understand that for sure we're going to be impacted um, in the sense that we cannot meet in person as much as we would like to. So that's the biggest impact. We are not going to be able to get things done efficiently. But luckily, First knows this, and I think recently has released a statement saying that the season is going to be stretched out. So we'll have more time to build, program, and practice. So that was the last question. I think that'll be all for today. And I hope you learned something from this TeleOp presentation, and at the very minimum, learned how you can drive your robot and program an arm. But hopefully more than that too.